Good morning. So here today in this lecture I am going to discuss about very few practical applications of linear time invariant systems driven by random process. Okay. So basically these are nothing but cross correlations because we use the cross correlation mostly. So we can also call it as few applications of cross correlation. And here I am discussing 4 applications. One is system evaluation. You are given a black box. You are supposed to find its impulse response or frequency response of the system, any of these things. Okay. So in this lecture we estimate the impulse response of the system. It is an unknown system. You are supposed to find you are supposed to estimate basically. Okay. You may not get exact impulse response. You are trying to estimate as faithfully as possible. Okay. Then target detection by radar and sonar. It depends on the again cross correlation principle. You are going to transmit some pulse kind of signals or any kind of signals, and you receive the echo signals from the target. You are cross correlating here with the transmitted signal, the echo signal. So echo signal is not in your control, but transmitted signal, it has a reference, correct? Because the transmit itself is generating the transmitted signal. It all has the references, that is phase of the carrier signal it has, and it has the beginning of the pulse, okay, pulse alignment, what do you say, synchronization, okay, pulse synchronization, all synchronization signals and all synchronization signals and phase values are available, okay, for each cycle and for each cycle of carrier also. It is available with the transmitter. Now, bit detection in the digital communication system, same thing. If you apply the coherent detection, so anywhere when you try to detect, it is a binary detection problem. In digital communication, we transmit zeros and ones. If 1 is there, signal is present. If 1 is not there, signal is not present. That is one way. Okay. So I mean, for amplitude shift gain signals, okay, other things phase and frequency a bit different, but they are also binary basically. There you are dependent on the phase. If phase is 180 degrees, 0, phase is 1 means 0 means 1. Okay, 1 and 0 there also. Similarly, frequency shift keying also, F1, F2, 2 different frequencies you are transmitting for 1 and 2. So in all these cases, you have a binary detection problem. That means whether it is a bit 1 or bit 0. So that is the bit detection. So these bits are transmitted as waveforms, bipolar waveforms, mostly bipolar wave. It must be bipolar waveforms. Otherwise, channel will be overloaded. Okay, that means the signal is passing, the mean value should be 0. The channel will heat up. Okay, so because DC won't contain, it is DC you cannot transmit anyway, but unnecessary it will heats up the system, even the antenna also. Okay, so that is what, so you always have the bipolar signal there. Then frame synchronization, or I should say training sequences also. Frame synchronization and training sequences. Training signals. So these training signals are also transmitted before especially in data communications and wireless channels mostly. And when you are transmitting signals, the channel will change. Time varying channels there. They are not, their impulse responses are not same. They change, sometimes they change during milliseconds. Okay, when you take fading channels, which we come across in wireless transmission, fast fading, slow fadings are there. So accordingly, the impulse response sometimes it changes slowly, sometimes it changes very fast. So you have to estimate the impulse response of the channel. It is nothing but channel estimation problem. And you have to, after estimation of the channel, you are supposed to compensate by using the equalizers. So these training signals are used for training the equalizer. That means basically it is channel identification. Once you know the channel, you are cancelling out the channel effects basically. Okay. So in that way, you can reduce the what you call as a inter-symbol interference. Okay. Basically, there is a meant for that. And you know exactly the where to sample. Okay. Where it is once this is get ridden off, you have again bit clock is there. So frame clock, bit clock, word clock, you can have different levels of synchronization mechanisms. And so there where you have to sample that also, you will be interested in all these things. Okay. So even in case of target detection also, you have a pulse where you should sample. Okay. We'll discuss more about those details. And here I have shown one system whose impulse response is h of t but unknown. So my job is estimate the unknown quantity, that is h cap. Okay. So I'm going to estimation. I'm going to do the estimation of the impulse response of the system here. So for that, what I'm doing, I'm inputting the unknown system with a white noise. I should say very clearly white noise here. Not only uncorrelated, basically totally uncorrelated means naturally when there is no correlation between two functions, cross correlation is 0. Okay. So then I should say what happens to the impulse response. Okay. What happens to the impulse? Okay, we'll see that. So here, this is the system under test. I am driving this system with the input process. At the output, I have another process, output process, and I am feeding the input process and output process to a cross correlation device. So this is nothing but integration x, then y, etc. Okay. So basically I'm multiplying this because we are basically checking the orthogonality of this by multiplying these two for a different time instance. Okay. So I have the cross correlation function here at the output, and this is also this is also estimation, correct? Because we can estimate this. We can estimate because we are measuring here. This is R cap. I am trying to find the cross correlation of input and output. I am trying to estimate the cross correlation because no tools are available. I am not aware of the input signal. Okay. I'm not aware of the system basically here. Okay. So that's why this system will output the estimation of the cross correlation between x and y. Okay. So that is nothing but, of course, here yx, I can also take xy. Okay. So let us take xy instead of yx because in diagram I have shown here. In the equations I have a different thing. So here this is what is this? This is nothing but the convolution of input. This is nothing but the convolution of input with the impulse response, unknown impulse response. Now you substitute this equation with this. Okay, this is the measurement. Keep aside. Analytically, let us see. So this is, I'm substituting it here. Then not I am taking out. This is the delta function. So this is what I already know it actually. So this I know already. And that's why this is estimations. That's why it is approximately equal to. I cannot say that it is exactly equal to, identically equal. It is approximately equal to. Equality is here, approximation only. Okay. So this is the measured quantity available with you, and you know the power spectral density, constant power spectral density of the input. That means input power, because input you can always measure the power. Okay, because it is in your hand. So this constant multiplied by this cross correlation is equal to the estimated impulse response of the system. Okay, so that is what you have. Now I am just taking this hf tau to left side. Hf tau equal to Rxy multiplied with some constant, which is proportional to the input power. Okay. So that means now I have estimated. Other than this, other than the white noise, if I put some other noise here, it is not possible to estimate the, at least so easily, it is not possible. Okay. The estimation becomes a bit complex. So, but in general, we use always white noise in this kind of system testing. Okay. Now, target detection by radar or sonar. Sonar is sound waves you are transmitting, and there is underwater communications or underwater distance measurement. Okay, it is basically the range measurement. And let us take here one. Let us take one ground here. Let us take one microwave dish kind of thing. So on Earth station, this is the beam, which is illuminating this area. In this one, we find the most of the power. And let us say I have some kind of target here. Okay, and this is at a distance r from this. So you are transmitting one pulse here. Let us say periodic pulse, not only one pulse, like that several pulses you are transmitting. It may be as a burst or it may be continuously. Okay, it depends on the type of radar used. This is basically a radar system I am explaining. So the target is at range of R. This is electromagnetic radiation. Of course, if you want to transmit a pulse, because it cannot, free space won't support it. So you have to modulate it with a high frequency where the attenuation is less by the free space. Okay, so this is nothing but modulation, pulse modulation. I transmit it here. Then it is reflected by the target. Again, signal comes back. Okay, I will get some kind of these things, some kind of these small things. So these are echoes. This is the transmitted signal. This is the echo signal. The starting of the echo signal, because these are synchronization, you can know easily, because starting point of this you are transmitting, and with respect to this, I am displaying with respect to this starting point of the pulse at the transmitter. So this, what is happening? This pulse is going there, again coming back. What is the total distance it is traveling? Total distance it is traveling is 2r divided by velocity of light. So this is nothing but time delay. Okay, this is velocity of light. It is the delay tau. That means it is the echo comes after tau seconds. Okay, if there is a target. When there is no target, no echo comes. Now what my job is to identify this location, and this tau. My parameter of interest is tau. Why tau? Because I want to find the range here. So take this side. So R equal to, I can write R equal to C tau by tau. Okay. So if I C tau by 2, if I find the tau, I can find the range. R is proportional to tau. So that is the radar basic principle. So what I have to do, how I find the time instant? This time instant I have to find. Okay. Now what I will do, the echo has come. So echo, let us say this is the echo is y of t. Transmitted signal is x of t. So I have to correlate these two. Okay. So when I correlate, what happens? I will take the same signal here. So here, when I correlate with this is the transmitted signal. Okay. At this point, so see what happened here. The pulse width, let us assume that pulse width is same, but because of attenuation, the amplitude of this echoes very small, maybe 1000 times, sometimes 1000 times, 10,000 times lower. That means 40 dB down. 30 dB down minimum. So that kind of situation you come across. So what you have to do when you are correlating transmitted signal with the received signal, you should reduce the power of this. Okay, you should take 1000th power. Okay, your scale down version of the transmitted signal you take and do the correlation operation. So this is also rectangular almost. So two rectangular pulses if I take, I will get a triangle as the cross correlation function. Okay, so it will be something like this. Some noise things, something like this. And of course this here I have not shown this gap more. So that's why I will face. So this is what now I have to sample at this point. This is the point, cross correlation. That is the point where the signal integrates and noise effect is small. Okay, of course, similar thing can be achieved by using it is equivalent to a matched filter, but performance wise there is a difference. But philosophy wise, because you know the wave shape, transmitted wave shape. Okay, otherwise you cannot find this. Okay, you cannot find because you know the shape. Then you can correlate both. So it is not called autocorrelation because the echo signal is different. Its frequency components might have been disturbed also. It is grossly both are same, but if you closely see, they are not same. If they are corrupted with noise, transmitted signal is not corrupted with noise. Okay, I mean maybe minute noise in the transmitter, so which we don't consider for signal processing purposes. Okay, so this is what you have, and for another pulse corresponding to another pulse, I have this, and corresponding this pulse again I have this. So sample here. So that is what is. Then what you will do? You put a threshold on this. Okay. So you have, let us say, at this point you have something like this. Then you are sampling here. Then you put a threshold here. On this sample, if the sample value is more than threshold, you say that the pulse is present. That means echo is present. Otherwise, echo is not present. Okay. So that is the detection problem. So binary detection here. And here the cross correlation plays very, very important parameter. So to get this cross correlation in a better way, okay, which is robust to target movement and other parameters are there. So we talk about ambiguity diagram and all those things. There is a different subject. So, but the cross correlation plays very, very important and is the key for the signal target detection. Okay. In fact, any signal detection, you can always, if you know the nature of signal, you can try to detect the signal using the cross correlation function. Now, let us similar kind of situation. I have something like this. Something like this. So this is, let us say this is 1, 0, 0, 1, 1, 1, 1, 4 ones are there. Of course, there is, if you can use something else, okay. Phase modulations are, okay. Or you can say ASK 0. So this is bipolar, basically bipolar signal after you're transmitting +1 -1 use. And here, where this is 1 is detected or 0 is detected. That is what you have to find. So this is similar to radar problem. There are also detection problem. But here, there you have at least pulse on period is very small. The duty cycle is very small. So the total cycle period is very large. Let us say 100 microseconds. If it is 10 kilohertz pulse repetition frequency, you have 100 microseconds, whereas this one has only 0.1 microseconds or 100 nanoseconds, 10 nanoseconds, like that, depending on the band and radar application. So that is what you have here. And here, that type of on-off relaxation is not there in the cycle. So every period is a valuable period for us. Okay, that's why we go for, I mean, this cross correlation receiver also is in the same philosophy. So if you have, you not only use the rectangular pulses, you do some kind of pulse shaping. It can be some raised cosine pulses, or it can be Gaussian pulses also. So that kind of to reduce the ISI. So after taking all these things, you have to do somewhere you have to do in the receiver the cross correlation. Okay. And where in the receiver is not a main criteria for this application. So somewhere in the receiver you have to, it can be done at RF level nowadays, at IF level, and at after detection also we used to do that. They are called non-coherent receivers. Then there is a signal to noise ratio loss will be there by 3 dB. If you use coherent detection, these are all detection, correct? Coherent detector if you use or cross correlation is a coherent detector basically. If you have carrier synchronization properly. Okay. So this is the kind of things which are regularly, I should say, you cannot avoid this kind of cross correlation. Without this, there is no digital communication systems. Okay. Then fourth application is training and synchronization in communications. So basically, there are some systems like V27 ITU standard, ITU speech codecs. I remember long ago I worked on this. ITU T30, for example, is a fax protocol, and I have I think 42. Okay, it is a QAM constellation, and V25 is FSK. I think the V21, V25, V21. Then I have V37 or something like that. So some ITU codecs are there. There are data modems. So there you are transmitting the data. For example, you take fax, transmitting the data page by page, line by line. So there is a lot of frame synchronizations are needed. So when to start the line, when to stop the line. So that kind of things will be there. And even in the communications also, you have the data and you divide the data in frames. Okay. And if you take, for example, time division multiplexing, if I take, you have to invariably divide the data in terms of slots. Okay. And within the slot also, you have so many frames. Okay. And there, at the beginning of the data transmission, let us say data transmission takes 500 milliseconds. I'm not talking about 1 second and other thing. Data transmission was some amount of data you want to transmit in 500 milliseconds. But if it is a wireless channel, and the wireless channel may change, maybe in urban regions, and where the channel is exposed to some kind of fading kind of thing, because of multipath signals also you will get it. And because of that, let us say every 10 milliseconds, the channel is changing. Channel is changing means channel impulse response is changing. So what you have to do? Transmit some data. Now by the time you transmit some data, 10 milliseconds data, after that channel, you assume that it is changing. Okay, actually it is continuously changing, but the change is very small. You can take discrete, consider it as a discrete changes. And after 10 milliseconds, you have to estimate the channel. You have to estimate the impulse response of the channel, the way, as I told you. And for that, we use, training sequences. So using those training sequences, because training sequences are known sequences and they are part of some preamble, we say preamble and okay, they are put together in the beginning of the data. So it is some kind of header, and there all data is known. And for carrier synchronization also, you will transmit a clean sine wave with the phase at which it was transmitted at the transmitter. Okay, that kind of phase also. So here you detect the phase from the preamble, and in the same way synchronization you can achieve. And here we use, in several places we use pseudo noise. So they are nothing but pseudo noise sequences, mostly maximal length sequences. So by using the kind of sequence, for example, if I take 1 1 1 0 0 1 0, it is a 7 bit, and this is what is repeatedly transmitted. Few cycles of this is transmitted. Then first you have to lock onto this one. So here what you have to do, this sequence you know already. So this sequence this sequence here it is not echo basically. It is the received signal, I should say. It is not the target basically. Okay. It is a received signal. Then this is a transmitted signal and transmitted copy. This is known. So you cross correlate this known training sequence with the received one. Okay. This is known basically. I should write like this. It is a known signal. This is a known signal and unknown receiver received signal is long, whereas this signal is short, relatively short, and you slide along the receiver and you will get somewhere peak, because this whenever this is aligned, this sequence is aligned, you have the maximum here. If the sequence is aligned something like this, you will get. So this is 7 here. This is 1, something like that. Okay, 7 1 or 1 is equal to -1 in the waveform. So this is this kind of thing. Whenever you have in the cross correlation, whenever you find large peak, that is where the training sequence is there. Okay, so that is the for synchronization of. Then after that, start reading the data. That is one application. And another thing, you have to because known data here and alternate ones and zeros also you will use. Okay, that is a different kind of thing. So here I should say that basically synchronization purposes, I am using some kind of known pattern of bits, random bits, known pattern of not only one cycle. Sometimes I will say 4 or 5 cycles, several cycles I will transmit because of big noise, burst noise. If I lose some cycles, I have left over with at least one cycle. That's why multiple cycles I will transmit. Okay. So all these are training sequences, preamble, and the pseudo sequences. They all come under the header of the data communications part. And this is that there also at several things you find that you use the correlation. Okay, one example I have given here. So that is what is the another application. I think like this you have thousands of applications. It is not innumerable applications. It is really not very difficult to even summarize all these applications. Thousands of applications are there. So I have taken only few examples. To start with, 4 different examples I have taken. One radar, other one for communications, okay, other one for system identification. So like that I have taken different applications. Okay. Thank you. Thank you very much for your time. I will stop it here.
Like, share and subscribe. Hit the bell icon for more updates.